using the gas laws, let's take a look at this one at a time. First of all, you can't work the problem without the little blue box. The little blue box tells you that you've got a pressure of 1 atm to begin with, 20 degrees Celsius, and 1 liter. So that gives you an initial set of conditions that we're really going to have to pay attention to. So let's start with those. We've got an initial pressure of 1 atm, an initial temperature, Satan spawn, evilness. They give us temperature in Celsius, which we know we should reconvert right away to Kelvin here. Then, and it should be, I'm going to write it over here, 293.15 Kelvin. Your volume is 1 liter. And this information will apply to the first 3 parts of the problem. So let's go ahead and take a look here. In part A, they want to know what will the pressure inside the container become if the pistons is moved to the 1.8 liter mark and the temperature is constant. So they've given you a second set of conditions, and in this second set of conditions for part A, they've told you you've got a second volume of 1.80 liters, and they want to know what the pressure is if the temperature remains constant. We have 2 of something, right? We have 2 volumes, so we're going to have to use the combined gas law. Whenever we have 2 of anything, we always use the combined gas law. So, I'm trying to find some place to put it here. We've got P1 V1 over N1 T1 equals P2 V2 over N2 T2. They just told us that the temperature isn't changing, so we can get rid of the temperature. They told us nothing about our number of moles changing, so that doesn't change. So we're left with P1 V1 equals P2 V2, which means that we just have to plug and chug here. We have an initial pressure of 1 atm. We have an initial volume of 1 liter. We have pressure 2 is 1.8 liters. Volume 2 is 1.8 liters. So you've got 1 atm times 1 liter divided by, because we have to get that P2 by itself, divide both sides by 8 liters. So 1 divided by 8.18 liters gives us a pressure of 1 divided by 1.8 gives us a value of P2 of 0.55555, and they're giving us only 3 sig figs, so 0.556 atm would be the pressure for part A. Let's clean things up a little bit before we do part B. Okay. Part B. The sample gas has now returned to its original state, so we've reset our conditions. What is the gas? What is the pressure of the gas? What will the pressure become if the temperature of the gas is raised to 200 degrees Celsius and the piston is not allowed to move? So what they're telling us there is that since the piston isn't allowed to move, that means that V1 equals V2. We've got a new temperature now of 200 degrees Celsius, and we won't be fooled by their evil machinations. We will convert right away to Kelvin, and that gives us a T2 of 473.15 Kelvin. And they want to know what the new pressure is. Once again, we've got two of things, right? Since we have two of things, we're going to be using that combined gas law. P1, V1, N1, T1, P2, V2, N2, T2. Number of moles doesn't change. Volume is not allowed to change. So we're left with P1 over T1 equals P2 over T2. So there's our formula, so it becomes a matter of plug and chug here. Our pressure initially was 1 atm. Our temperature initially was 293.15 Kelvin. They're wanting to solve for our new pressure when we increase that temperature to 473.15 Kelvin. So that gives you 473.15 Kelvin times 1 atm divided by 293.15 Kelvin. And I get 1 point, yeah, 1.61. P2 is 1.61 atm. All right. Let's keep going and take a look at part C. Part C, the gas described in part A and B has a mass of 1.6. What is the most likely? The sample is most likely what monatomic gas? So, we've got a pressure of 1 atm in part A, a temperature of 293.15 Kelvin, and a volume of 1 liter. And we're needing to know the number of moles if we're to figure out what gas it is. Why do we need the number of moles? Because we can figure out molar mass once we have number of moles and the mass of that gas. So we have to calculate the number of moles. Well, that means we have one of every variable. So we can use Pivnert. So I've got PV equals nRT. So it becomes an issue of plug and chug here. So I've got, whoa, that was a marker. Oops, there we go. 1 atm times 1 liter equals N times the gas constant, 0.0821 liters ATM moles Kelvin. If you're asking where that gas constant came from, you need to go back and review the lectures. This is one of the things I told you to memorize in lecture. Come on. Times 293.15 Kelvin. Well, we have to get N by itself. Divided by 293.15 equals 0.0415 moles. Once we have our number of moles, we then need to figure out the molar mass of the gas. Molar mass, remember, has units of grams per mole, and that tells you how to solve for it. You take that mass they gave you, 1.66 grams. You know that mass of 1.66 grams is equivalent to that number of moles you just calculated, 0.0415. So you divide 1.6 by 0.445, and that gives you 40 grams per mole. You go to the periodic chart and you discover that means it's argon, because argon has a molar mass of 40 grams per mole. Alright, so let's take a look at part C now. Clear that up here. Oh, I'm sorry, part D. That was part C. Part D, assuming ideal behavior, how many moles of argon would you need to fill a 14.5 by 12 by 10 foot room, assuming the atmospheric pressure of... Alright, first things first, let's deal with the volume. Volume is length times width times height. So the volume is 14.5 times 12 times 10, and that is going to give you 14.5 times 12 times 10 equals 1,740 feet cubed. And, oh, they are very nice. They give us a conversion factor between cubic feet and liters. So we can take that right away and convert to liters, which means we can then go to PivNerd. According to what they gave us in the problem, 1 cubic foot is 28.2 liters. So that gives us 4906.8 liters is the calculator number, but we only have 3 sig figs, so let's move it into scientific notation. 4.9068 times 10 to the 4th liters. So now it's just a matter of PivNerd. So we've got 1 ATM times 4.9068 times 10 to the 4th liters equals the number of moles times 0.0821 liters, ATMs, moles, Kelvin, times our temperature, which they told us was 20 degrees Celsius, which is 293.15 Kelvin, and then you just solve for your number of moles, which gives you 2.0387 times 10 to the 3rd moles, which is a lot of moles. A lot of moles. Molicifant. Ooh, I have been watching Descendants with my daughter over this break. But anyway, that's that for that problem.